Good day and welcome to this podcast entitled Drug Synthesis. This is part of the medicinal chemistry program of the NCSSM online uh, department. What we'd like to talk about in this podcast is continuing our discussion on how about making drugs. By now, you really should know about these considerations. A drug must be able to be absorbed into the body, and we call that A, absorption. The drug must be distributed to the right target, so D for distribution. We must know how the drug is metabolized, and that is M for metabolism. And we must know how the drug gets excreted, and that's E for excretion. So this is the ADME system that we've been talking about now for several weeks. And we also must understand, of course, the toxicities of the drug, or T, so ADMET or ADMET. So in terms of making drugs, a big part of how a medicinal chemist spends his or her time is being able to get the drug absorbed, getting it distributed to the right target, getting it, figuring out how it metabolizes either in a good way or not a good way, figuring out how the drug gets excreted, and making sure that they understand the toxicities of the drug. Okay? What we've not talked about so far in this course, which is the subject of this conversation, is a little bit about how we actually make the drugs. A question was posted a couple weeks ago, and the question was basically, is this really what medicinal chemists do? And I think that question was being asked in response to all of the statistics and all of the data analysis that we've been doing so far. And if you recall, my reply to that was, yes, this is partially what a medicinal chemist does, but some medicinal chemists also synthesize or actually make the drugs in the laboratory that are then used, that are then tested on animals and eventually on human beings. Clearly in an online course, or certainly in a course like this, we don't actually have you in the lab synthesizing medicines. It's outside the scope of what we're trying to do in this course, but you do need to understand something about it. So drug synthesis involves the use of organic synthesis, and that's going to be the topic of this conversation today. So basically what drug synthesis is the conversion of existing molecules into other useful molecules. And it's a series of steps that leads from one or more starting materials, and it culminates in a finished product. So basically what you want to do is you want to start with compound A and eventually end up with compound B, C, D, E, or even Z somewhere down the line. So you're starting with some starting materials and you culminate in a finished project. In terms of drug chemistry, what we're most often doing is we're converting little molecules, often called the lead drug, into some sort of bigger molecule, which is actually the therapeutic drug that we end up giving to the patient. And another thing that we do a lot in drug chemistry is we synthesize unnatural products from natural products. So many of our drugs, as you recall, start out as compounds that we are able to extract from plants or microorganisms or marine sources or other natural production pathways, and then what we do is we have to modify them to make them do more closely what we want them to be able to do. And certainly we've heard us talk about it. We've done some activities related to modifying existing structures. So you've done some things like you've taken a benzene ring and you've added a methyl group to it, and you've measured to see how that affects its toxicity or its ability to absorb. So in drug chemistry, we do an awful lot of modification of existing structures. And you've been doing all of that so far, basically without any sense of that somebody actually has to do that in a real laboratory. And this talk gives you a little taste of how that happens. Okay, so here's an example. Here's Taxol, which is an anti-cancer drug. And it's also a very rare natural product. In other words, we can't go out into nature and cut down some plants or extract this drug from a fish or some other organism. Okay, this drug needs to be synthesized. It starts out as a very small molecule, and when we finally get to the point where we have Taxol, you have the synthesized molecule that you see in front of you. And this is a very elaborate organic synthesis. I won't ask you to look at any molecule, certainly of this size, but this is what medicinal chemists have to figure out how to do on a regular basis. Okay, here's a little simpler example where on the left I'm taking this molecule cyclopentadiene, and you should be able to figure out why that is a cyclopentadiene. 5 carbons in a circle, so cyclo. The diene means there are 2 double bonds, so we have a diene, and what we need to do is be able to synthesize this drug into indinoprost, which is a platelet aggregation inhibitor, meaning basically it's an anticoagulant, very much like aspirin is. So the people that work in organic synthesis labs need to take something like cyclopentadiene, and by engaging in a series of organic synthesis steps, they end up with the drug that you see on the right-hand side. Okay, some general guidelines on how they do this, a little bit about methods and strategies. Certainly one of the things that one has to do is we have to either form carbon-carbon bonds, or carbon-carbon double bonds, or carbon-carbon triple bonds, or we have to remove those bonds. We have, for example, turn an alkene into an alkyne. So certainly being able to form bonds or break bonds is an important thing that we have to be able to, an organic synthetic chemist needs to be able to know how to do. There's an awful lot of functional group interconversions, or FGIs, that have to take place. So functional group interconversion, as the name suggests, might mean something like changing a carboxylic acid to an ester, or changing a carboxylic acid to an alcohol. Okay, so we convert these functional groups into something that they weren't when we started. Okay, and the way we do that, there's a variety of processes. Some of you might remember redox reactions from your basic chemistry course. So oxidation reduction reactions are a very important mechanism by which we do this, which is why we teach redox at the earliest levels of chemistry. We can certainly substitute in functional groups. If we don't have a functional group, we can substitute what is there for what we want there. We can eliminate functional groups, so we can get rid of the ones we don't want. We can add functional groups. That's called addition. No fancy name there. So these are all different types of things that we can do to get functional groups changed into what we actually want them to be. And there's other kinds of functional group interconversions that we won't get into all the details here in this talk. We can also make skeletal rearrangements. Okay, we can push atoms around. We can change things inside the molecule, so we can basically rearrange the skeleton of the molecule so that it looks more like the molecule we need it to be, or does more of what we need the molecule. So we can take what is already existing in the molecule and just basically do a rearrangement. There are also times, and the book talks about this in one of the early chapters, something called protection or deprotection. Let's say, for example, I have 2 carbons in a molecule, and one of those carbons, I want to do something to it. I want to oxidize it or reduce it. I want to substitute something onto that carbon. I want to eliminate something on that carbon. I want to add something on that carbon. But in the reaction mechanism, okay, if I'm not careful, the second carbon will also get changed. And it's often the case that I want to make a change to the first carbon, but I don't want the second carbon to change. I want that to stay just like it is. So I have to add what's called a protecting group to the second carbon to make sure that it doesn't change when the reaction happens. And then when I'm all done, if I need to, I can remove the protecting group, and I'm back to where I was. So a protection is being able to prevent changes to carbons that I don't want changed, while some other carbon that I do want changed actually gets changed. You'll read about that in the book and see some examples of that. Okay, what do you have to know? You have to know a lot, and this is why you will take at least a year's worth of organic chemistry at the undergraduate level. If you stay in this line of work, if you stay in pharmacology, you will at least take an advanced course. You'll take advanced organic chemistry, either as a senior in college or as a graduate student. And you have to know an awful lot. This is a very hard science, and it requires you to know a lot. You have to know there exists in organic chemistry synthesis what we call named reactions. So reactions that have somebody's name attached to them, meaning usually the person who discovered them. Okay, so for example, the Beckmann rearrangement. You see the product on the left there. Basically, I've got an alcohol group there in the presence of concentrated sulfuric acid and a little bit of heat. That's what the triangle there means. I end up with this substituted amine group and the formation of a carbonyl, the C double bond O. Okay, so I have the Claisen condensation where here I've got two esters, and I'm adding to it a sodium ethyl ether compound also in the presence of strong acid, the H3O plus there. And what you see there is I basically get the diketone. So I'm basically rearranging. I'm not adding anything. I'm basically rearranging or condensing, excuse me, I'm not rearranging. I'm condensing the molecule on the left to form the molecule on the right. Those of you who, I think, we did this in the computational chemistry class, we did a Diels-Alder reaction where you see I have a butadiene and an ethene combining in the presence of heat to form the ring structure that you see on the right. So that's a Diels-Alder reaction. Okay? And you need to understand that there's lots of these reactions, and if you look online and look for named reactions in organic chemistry, you'll see a long list of these types of reactions. And you have to know these named reactions because you have to figure out which one to use at the right time. Okay, so here's a quick example. Okay, here's my target molecule. Okay, I'm trying to form this aldehyde there. Okay, and you see the starting material over there on the right. Okay, so here's my analysis. My analysis says I don't have any change in the number of carbons. I don't need to add any carbons. I don't need to eliminate any carbons because I have the same number of carbons in both molecules. Okay, I do, for my functional group interconversion, however, I do need to change an alkene. Okay, and you see that the alkene over on your right. Okay, I need to change that alkene there to the aldehyde. Okay, so that's my functional group interconversion. And now the question is, what reactions do I know? Well, I know a reaction that's called an alkene ozonolysis. Lysis means to cut, and ozone means we're doing that with ozone or O3. The problem is, so that might be one of the reactions I think about using. The problem is that particular reaction, and I would have learned this in my organic chemistry class, is that it alters the carbon count. So that reaction might change the alkene to the aldehyde, but in the process of doing so, it changes the carbon count, so that's probably not a good reaction to use. Okay, I can oxidize, I can do oxidation of a primary alcohol, and that will, the advantage there, of course, is the carbon count is unchanged, so that may be a possible mechanism by which I can do this particular synthesis. Okay, so what I'm going to do is think about using something called retrosynthesis where I work backwards. So what I have here on the left is the target molecule, and I'm working backwards from the originals, okay? And you see the arrows there with two bars on them. That means that I'm sort of working backwards. Okay, so I'm going to choose the oxidation of a primary alcohol, and again, the double arrow represents a reversal of the process, and this is known as retrosynthesis again, or thinking backwards, and E.J. Corey at Harvard came up with this, and he was awarded the Nobel Prize in Chemistry for this in 1990. So this is a fairly recent procedure or thought process, okay, and here's a retrosynthesis definition. Problem-solving technique for transforming the structure of a target molecule to a sequence of progressive materials along a pathway, which leads to a simple or commercially available starting material for chemical synthesis. That's E.J. Corey's definition. Basically, it means retrosynthesis is working backwards. Okay, so I'm going to do that. I'm going to work backwards, and then once I have the primary alcohol, I can do a process called hydroboration. That's another one of the mechanisms that you would have learned in organic chemistry. And that answers the question, can we make the alkene from the alcohol? Okay. And the reaction again that I use is hydroboration there. And you see the entire pathway there of hydroboration going from left to right. So you see I have the C double bond C alkene. And in the presence of a couple reagents like BH3 and THF, okay, what I get there is a substituted compound. Notice the double bond of the carbon-carbon has been broken. Okay, so now I no longer have an alkene. Now I react this with hydrogen peroxide, H2O2, in the presence of a strong base, OH negative, and that gets rid of the BH2 and attaches the OH group onto the carbon. And so this is the synthetic process by which I have changed a alkene into an alcohol. So you see there it's sort of a two-step process, reacting first with the reagents BH3 and THF, and then reacting with peroxide and a strong base to get the final alcohol. Okay, so if I look at this whole process in a retrosynthetic way, what you see there is what's on the top, okay, sort of going from the target on the left to the starting on the right, and the entire retrosynthesis is shown underneath there in a little bit more detail. And now if I flipped it around and show the actual forward reaction, you'll see that the first step is taking the alkene, reacting it with BH3 peroxide and sodium hydroxide that gives me the alcohol. And then I react it with another compound called pyridinium chlorochlorate, PCC, and that gives me my aldehyde. So that would be the synthetic pathway by which I create this particular compound. You may not be able to see this slide very well. You could find this anywhere on the net. This is sort of the 12 essential organic reactions. These would be the organic reactions that you would absolutely have to know, and we drill this into you in organic class, and you can talk very intelligently about these reaction types by the time you get out of your organic chemistry class. In an advanced class, you would go even more detail into these reaction mechanisms, and there's lots more than just 12. But these are the 12 essential ones, so you can get a sense that we have some organization for helping you learn these things. Okay, as an example, let me go back for a second. You'll see in there one of the examples is what's known as an electrophilic addition. So I give you an example there here. Okay, so here's an electrophilic addition reaction. So I'm going to react an alkene there. You see the C double bond C there. And I'm going to react it with hydrogen bromide. And what happens is we lose one of the double bonds. It goes over to the hydrogen, and that releases the bromine, and the bromine now becomes an ion with a lone pair. And notice what's happened in the middle compound to one of the carbons. It now has a plus sign on it, and that is called a carbonium ion. So the bromine with its negative charge will now attack that positively charged carbon, and eventually we have the addition of the bromine to the carbon. So basically the steps are the addition of what's called an electrophile, the H+, to the alkene. So we add that hydrogen plus to the double bond, and that hydrogen plus is called a nucleophile, and that forms a carbonium, or the carbocation is probably a better term for it. Okay, and now we have the carbocation, which is an electrophile, reacts with the negatively charged bromine, which is a nucleophile. Okay, so some new terms there. And the final product is the bromoalkane, and that's called an electrophilic addition reaction. Okay, some of the new terms there: electrophile, as you might suspect, is an electron lover, and that's typically a positively charged ion like H+. A nucleophile is a nucleus lover. Remember, the nucleus has a positive charge, and that's typically a negatively charged ion like bromine negative. That should say charged ion there, not IO. An electrophilic attack is that reaction mechanism where electrophile attacks or reacts with a nucleophile, and a nucleophilic attack is just the opposite. Okay, so these are terms that you're going to run across, just like lipophile and hydrophile, or lipophilicity and hydrophilicity. You're going to run across electrophilicity and nucleophilicity as terms in these reaction mechanisms. And the carbocation, again, is an abbreviation for carbon and cation, and a cation is a positively charged ion. So a carbocation is a C plus site or C positively charged site in a molecule. Okay. All right, so here's a simple example. Here's the organic synthetic pathway for forming aspirin, also known as acetylsalic acid, or ASA. Okay, what I do is I take the phenolate ion, that's the first compound there at the top left. That's the one with the oxygen on it with the 3 lone pairs. There are dots there, those are electrons, negatively charged. So we react that in the presence of CO2, which you also see pictured, under pressure to form the ortho-hydroxybenzoic acid, or the salicylic acid. And the hydrobenzoic acid is the compound that's in the second row on the far right. So I skipped a few names there. And the arrows there are trying to show where electrons are moving. So you can see, for example, one of the bonds in the ring gets moved to the CO2, and that CO2, one of those bonds gets reformed, and now the CO2 is connected to the benzene ring, and then some of those hydrogens now move around a little bit. Now in the presence of hydrochloric acid, which you see pictured in the middle row, that gives us the salicylic acid. And now what we're going to do in the bottom row is we're going to add an acetic acid, okay, that's the CH3 sub C double bond O, 2O there, and that's going to be an addition reaction, and that's going to give us the acetylsalicylic acid. Okay, so I'm sorry, with acetic anhydride, I think I called that acetic acid, acetic anhydride to form the acetylsalicylic acid. So there's basically the complete organic synthesis method for starting from a phenolate ion, being able to end up with the ASA, acetylsalicylic acid compound. All right, that's a really simple mechanism. Here's one that's quite a bit more difficult. Here's the synthesis of Tamiflu. And what you might want to go look at this on the web. There's a Wikipedia address there at the bottom for this thing. And I would encourage you to do that and go. This is also not a particularly difficult synthesis, but it's a lot more complicated than the one you just saw for aspirin. So what you should notice is what we're starting with and what we end up with at the end, and all of the reagents and the heat and the pressure and all of the other considerations that have to come into play to get us from the starting materials to the ending materials. Here's the second part of the Tamiflu synthesis. So you saw the first half in that back slide, and here's the second half in the second slide. Okay, it's a pretty big synthesis, but not horrendously big as others go. And that's the end of this discussion. We hope to see you soon. Thanks very much for listening. Goodbye.